Have a good night, Professor Russell. Buenas noches, Jessy. Buenas noches con todos los asistentes.
¿Qué tal, Shirley? Muy buenas noches.
Okay. Have a good night, Engineer Russell, and thank you for joining for this meeting. We are really pleased to come with you in this first International Congress of Geotechnical Engineering at Peruvian University of Applied Science. We are very pleased again for counting with your presence today, and we'd like to thank you in advance for letting us to learn from you and your experience by the topic partial saturation influences of the characterization and strength of silty tailings. Now, my partner is about to talk about the content.
Listo, muy buenas noches a todos los presentes. En esta ocasión, nosotros, el capítulo GeoUPC, en el primer Congreso Internacional de Ingeniería Geotécnica GeoUPC, vamos a presentar al ingeniero al que ya pudieron conocer ahora hace un momento, que se presentó. Por supuesto, el ingeniero Adrian Russell. Para el contenido, nosotros tenemos nuestra presentación del equipo del GeoUPC. Vamos a conocer un poco más al profesor Adrian Russell, un poco más de su biografía, para conocerlo, porque imagino que no muchos tenemos quizá conocimiento acerca de él. También veremos su exposición del tema Partial Saturation Influences of the Characterization and Strength of Silty Tailings. Y finalmente tendremos una ronda de preguntas al momento que acabe la ponencia. Como parte del equipo de GeoUPC, somos un equipo conformado por alumnos de la carrera de Ingeniería Civil de la Universidad Peruana de Ciencias Aplicadas UPC, y tenemos como razón de ser nuestra formación como profesionales en el ámbito de la geotecnia. Nosotros conformamos un espacio crítico y de investigación donde participamos y creamos actividades para la comunidad estudiantil con el objetivo de promover y fomentar nuestro desarrollo personal y profesional y llevar a cabo lo aprendido de manera teórica a la práctica. En este caso, acá tenemos el tema, que es Partial Saturations, Influences of the Characterization and Strength of the Silty Tailings, ¿no? Tenemos la presencia del ingeniero Adrian Russell, de Australia. El ingeniero es profesor de Ingeniería Geotécnica en la UNSW de Sydney, Australia. Obtuvo su licenciatura en 1998 y su doctorado en el año 2005, ambos por la UNSW de Sydney, Australia. Su primer nombramiento académico fue una cátedra en la Universidad de Bristol, Reino Unido, en el año 2013 al 2007. Becario del Consejo Australiano de Investigación, dedicado al 100% de su tiempo a la investigación sobre la licuefacción de residuos. Experiencia centrada en los ensayos de elementos de laboratorio de suelos y relaves, CPTs controlados en laboratorio y simulación de terremotos, caracterización de la geometría de partículas y poros, mecánica de suelos no saturados y teoría de expansión de cavidades y transferencia de conocimientos a la industria. Es representante de Australia en los comités técnicos internacionales TC106 y TC221 sobre mecánica de suelos no saturados y relaves dentro de la ISSMGE. Realiza trabajo de supervisión de expertos sobre la estabilidad de las TSF. En 2019 pasó una comisión de servicio de 6 meses con Pell Sullivan Maynick Ltd, proporcionando experiencia de proyectos de residuos mineros. Ha recibido distinguidos premios tales como Best Paper Award at ESQSU 2007, the Australian Geomechanics Society AGS Research Award NSW en 2011 y el Best Paper Award at Australia ACCM 2015.
Okay, thank you. Good night, Professor Russell. I'm gonna talk about your experience to the audience. Okay. Thank you. Okay. Our speaker today is got a bachelor degree and doctorate by the University of New South Wales UNSY by Sydney, Australia. He is nowadays a geotechnical engineering professor on the same university in Sydney, Australia too. He's now actually an Australian Research Council Fellow dedicated full-time to liquefaction investigation. He had his first academic appointment at the University of Bristol between 2003 and 2007. Now he conducts peer review work on the stability of TS. Also he is an Australian representative in international technical committees, TC 106 and TC 221. He has received distinguished awards like the Best Paper Award in 2007, also the Australian Geomechanics Society Research Award in 2011, and the Best Paper Award in Australasia in 2015. So now we are really pleased for your presence today, Professor Rosell. We now having a really good night with your conference.
Oh, look, and thank you for inviting me and hosting me to give this talk. I'm really pleased, and I'm really pleased that there's a big audience here, mainly of students as well, because we have to train the next generation of engineers to deal with some very difficult problems. So I'll be talking about that tonight. So should I share my screen now?
Yes, please. If you'd like to begin, we are ready for you.
Now, can you see my screen?
Yes.
Good. Okay. Look, thank you for the introductions and for this opportunity. So my name is Adrian Russell. I'm from Australia, and I will obviously be speaking in English. I'll talk quite slowly, so hopefully you can understand. My topic is about tailings, and in particular, partial saturation. What does that do to strength and critical state? And how can we deal with it in practice when we look at interpreting cone penetration tests and when doing stability assessments of tailings dams and considering liquefaction and things like that. So part one of the presentation is about the mechanics of unsaturated soils and tailings. This is a very complicated topic, but I will try and show just the basic features of what is most important, and I'll do that in around half an hour, 30 minutes. And then part two, I'll focus more on the cone penetration test and strength of unsaturated soils and tailings. Look, I must acknowledge a number of partners who have helped put this work together. It was started off through an Australian government research project involving 4 universities and 6 mining companies. So this is a really big project, and that has finished just recently, but I'm continuing on that work on my own, again with some government funding as part of a future fellowship. And this is a strange position where, although I'm working in a university, for 4 years, I just focus entirely on research, so I don't have to do any more teaching just for that period of time, so I can dig very deeply into this problem and help come up with some solutions that will help industry. Just briefly about UNSW, the University of New South Wales. It's in Sydney. It's very near the beach. There's Bondi over here. Coogee, it's a famous beach. This is our university. We have around 60,000 students and 25% are international. It's primarily a technical university, so engineering is very big and strong. We have the largest engineering faculty in Australia and the best laboratories. And we rank first in Australia and 13th internationally for our civil engineering work. And in geotechnical engineering, we have 5 academics, 4 contract academics and research associates, and around 20 PhD students. And in fact, one of my PhD students at the moment is from Peru. So there you go. I'm very happy with him, and I'm always looking for more. So please contact me if you are interested. This is just a little bit about my history. When I was a child, I was raised on a farm in the outback, if you like. But my farm was here, my family's farm, and we were surrounded by coal mines. That these areas here are coal mines, and in these orange circles are tailings dams. So mining and tailings were very nearby and very present in our thinking and what we had to do. I went to Sydney, the big city, as a student and did my bachelor's degree at UNSW and also a PhD. But I've also spent some time in industry. I think that's very important, even if you're going to an academic career, to have some time in industry to learn those practical skills, and that was really valuable. And I've also spent some time at the University of Bristol in the UK, in England. UNSW, we've built up a laboratory specifically targeting unsaturated soils, but also looking at cone penetration testing and liquefaction in earthquakes, as well as under static conditions. So we have built a calibration chamber. We designed and built this ourselves, so we can do full-scale cone penetration tests in samples while controlling suction and confining stress and density and all these properties. And we also built an earthquake shaking table. We designed and built this ourselves, so it's low cost. It's less than half the price of something that you buy from a big supplier, and this permits both horizontal and vertical shaking at the same time. And my student from Peru is working on that right now, looking at liquefaction inside tailings. Let's get into part one of the talk, and it's about the mechanics of unsaturated soils and tailings. So I'll talk about what they are, and then the motivation and relevance for this work. And then I'll focus on the effective stress, strength, and suction hardening, and how we put that into a mechanical framework. And I'll highlight the importance of water retention, and then I'll show some strength and stability problems which demonstrate application, and this thing called the equivalent method, which makes that very, very simple to do. So what are unsaturated tailings? Well, they're materials where you have solid particles, but both air and water in the pore space. And they're widely spread in many engineering problems, in the civil sector, in slopes and dams and compacted soils, but also in the mining sector, in tailings, and also ore, when you transport the minerals and the products of your mining, they're often in a partially saturated state. And the behavior of these materials is influenced by a phenomenon known as suction. Suction, or S, is the difference between the pore air pressure and the pore water pressure inside the soil or the tailings. The air pressure is always larger than the water pressure, and that is possible because of a capillary action or a surface tension which exists across the air-water interface. Think of that as a skin, a bit like the rubber of a balloon. The air pressure inside the balloon or inside the tailings is larger than the water pressure outside of the balloon or near the particle contacts, because of this curved interface which has a tension. The air pressure is usually 0 atmospheric pressure, which means that the water pressure is negative and the suction is positive. And we put that suction, well, firstly, the suction literally pulls particles towards each other and increases the contact forces. And that's why we call it a suction. It's a type of pulling action. And we know that soils and tailings get their strength from particle to particle contact stiffness and contact force and friction. So the effective stress goes up because of this suction, and so does the strength. And we put the suction into the effective stress using this equation. This is the total stress. Suction is multiplied by chi, this curly X symbol, and that is a multiplier which accounts for the fact that the water doesn't act uniformly across the cross section of the material. And once you quantify the effective stress, you can put it into a strength equation in the usual way, and this is just the simple Moore Coulomb strength equation. You still have a cohesion and a friction angle, but suction is inside this effective stress. So drying causes suction and strength to increase. Wetting causes suction and strength to reduce. So this capillary action is very important, and it causes water to go into tension. These are capillary tubes. These are just open-ended glass tubes. This one has a very, very small diameter. This one a very large diameter. So we can consider this line through here, that this is water, but it is being coloured red just to help illustration. We can think of this water as being just a large body of free water. So the pressure is 0 at the surface. But inside this small diameter tube, the water gets sucked upwards because of the surface tension and the capillary action up here. So the water above this, let me see if I can change this to a pen. If I draw a straight line through here, the water in this region is in tension or a negative pressure, and the water below it is in compression, or it has a positive pressure, which is hydrostatic. And the distance that the water rises inside this tube is controlled by this equation, which is a function of the diameter of the tube. Theta is the contact angle between the water and the glass, and T is the surface tension of the water. It's a real physical property, and that is what controls the height of that water. And the same thing happens in soils and tailings. They have very, very small diameters of pores, which causes water to be sucked upwards sometimes, and the water to go into tension or have a negative pressure, giving rise to a suction. So where is this relevant in a tailings dam? Well, there are several places. Firstly, in the embankments. If they're above the phreatic surface, then they'll be partially saturated. Obviously, in the tailings body, if you're above the phreatic surface, they will also be, the tailings will be partially saturated. And possibly even below the phreatic surface. In this upstream construction scenario, if you're building segments of the dam on top of previously desiccated surfaces, and then the water table or the phreatic surface rises, that air in that tailings might stay trapped inside, and the tailings is still in an unsaturated state. And we obviously push cones into this tailings every 2 years or something like this to do our safety assessments, and large sections of those cone results may be through partially saturated tailings. So we need to work out how to deal with that. The suction and the partial saturation will also increase the strength and the pre and post liquefaction strength. So the peak or the large residual value. And we need to, if we want to do things accurately, account for that strength as well in our stability assessments. So when we account for suction, we can remove unnecessary conservatism in our designs, in our assessments, and we will achieve a higher factor of safety. And obviously, as tailings dams become very, very large, or if they're marginally stable, we want to do things as accurately as possible. If you assume a very, very conservative worst case scenario, which is unrealistic, the factor of safety might be 1 or less, suggesting that the structure is unsafe. But in reality, the factor of safety might be 1.1 or 1.2, suggesting it is safe. So we need to account for this suction to do things properly. And it also adds reliability and confidence to what we are doing. And often when you are designing and checking safety, you have a range of factors of safety that you're allowed to work within, depending on how confident you are with your assessment. So if you add confidence and reliability, you can move towards the bottom of that range and adopt a lower factor of safety. So let's look a little bit more carefully at the effective stress. Can you still hear me? I've just had a technical function.
Yes, Professor,
Oh,
we can hear you.
Good. Good, thank you. Okay, so here's the full equation. So suction is put here, and you can see that the multiplier chi is in front of it. We call that the effective stress parameter. And this part here is the what we call the total stress in excess of poor air pressure. And that part we sometimes call a net stress. And the poor air pressure is usually atmospheric pressure, which we use as a datum. So we set it to 0 often. The effective stress parameter is 0 if the tailings is dry. So that means that there's no suction influence, or it's 1 if it's fully saturated. So that means the air parts cancel out and you're left with the traditional effective stress equation down here for a saturated material. And this chi value is between 0 and 1 when it's unsaturated. This is the effective stress approach, and I'll show that it actually enables us to do some very simple calculations capturing suction. But I must also acknowledge that there's an alternate approach called the 2 stress state variables approach, which is a little bit more popular in North America. And they use things like the tan phi b and other terms. But that approach and this one are interchangeable when you just realize that the chi factor is the ratio between the tan phi b and tan of the effective friction angle. Okay, let's look at some typical triaxial test results. So I start with these two results down here. These are for saturated tests. This is on a decomposed granite, a silty sand, which is very similar to a tailings. The void ratio is around 0.4. So you get the classic strength increase, which approaches a strength at large strains, and there's no peak, if you like. It's a loose material, very typical. And we get a volumetric compression as we go. I've also shown another set of results, these two up here, which are for unsaturated tests. The suction is constant, either 100 or 200, and the void ratio is around 0.47. So they're actually looser than the 2 saturated ones. And you can see how now we're actually exhibiting a peak in the strength, which then flattens off to some residual value. We get a little bit of volumetric compression followed by a lot of dilation down here. So suction is making the soil feel denser and stronger, even though it's looser than the saturated soil. And I'll explain why that happens in a minute. But we know this, when we play with soil and we add a little bit of moisture, it does feel stronger. A couple of interesting things come out. When we look at the residual or the large strain strength or the critical state strength, if you plot it in the Q versus P plane all of the data collapses onto a single line. As long as we put suction into the effective stress properly, we get a single effective stress friction angle at the critical state. The same is not true at peak conditions. At peak conditions, we see that suction increases the friction angle by a small amount, between around 2 and 6 degrees. So, that's due to a phenomenon called suction hardening, which I'll explain on the next slide. So this is suction hardening. If we think about our normal consolidation lines, these are lines that you would measure in a odometer or a one-dimensional compression test, for example, or an isotropic compression test. If it's saturated and we plot the void ratio against the log of effective stress, we get a fairly classical response, a stiff part initially while the soil is over-consolidated, and then it becomes less stiff on a steeper line as it becomes normally consolidated. If it's unsaturated, the same thing happens. We have a stiff response initially, and then it becomes steeper and less stiff as it becomes normally consolidated. But suction is causing a shift of this normal consolidation line to the right. And we call this suction hardening. It means that the soil, when unsaturated, feels as though it is further away from the normal consolidation line, or in other words, it feels as though it is more over-consolidated. And that is why you see that peak strength in those unsaturated tests where you didn't see it in the saturated tests. The soil, when it's unsaturated, behaves more like an over-consolidated material. We call it hardening because these consolidation lines, they relate to the size of a yield surface in a cam clay type constitutive model. So they enlarge the yield surface through the pre-consolidation pressure. They enlarge the elastic region, which we, from a mechanical point of view, we call that a hardening phenomenon, hence the name suction hardening. So here are those normal consolidation lines. This is for the unsaturated state over here. This is for the saturated one here. But there's a companion shift of the critical state lines as well. Critical state lines are generally parallel to our normal consolidation lines, but they're shifted towards the left by some constant distance or some ratio. So if we get a shift or a suction dependent movement of our normal consolidation line, we also see that with our critical state lines. So this would be for the saturated case down here, and this would be for the unsaturated case over here. And I'll show some real data where we've measured that in some tailings in a moment. Here is that data. This is for a gold tailings at the top here. This is the saturated critical state line. And this ratio, you don't need to worry about it too much. I'll detail it later. But for different suctions, the critical state line shifts upwards and rotates a little bit. So this is it for certain suctions, and then for larger suctions, it's even further up here to the right. And this is another one for a copper tailings. Again, you can see how the critical state line is shifting or moving for different suction magnitudes. So we need specialist equipment to determine this. We need suction controlled triaxial machines, and then you can characterize the tailings. We can plot things like the friction angle in excess of the critical state value against the state parameter at the beginning of shear. And it doesn't really matter if it's saturated, which is the solid symbols, or unsaturated, which is the open symbols. All of the data more or less shows a unique trend. Now this state parameter is calculated using the relocated critical state lines when there is suction present. The state parameter, and you probably have learnt this, is the vertical distance between the current state and the void ratio on the critical state line at the same value of mean effective stress. So how do we determine this chi-s value and put it into our strength and stability calculations? I'll show how we do that in a very simple way, but we have to understand water retention. How does water occupy the pore space when there is suction present? And this is a general relationship that shows what happens. If we start with a saturated material initially where suction is very, very low or zero, and we increase suction gradually, then eventually air will begin to enter the pore space and displace the water. And the state of the material will move along what we call a main drying curve. So the soil is, or the tailings is becoming drier. There's also a main wetting curve down here, which is what is followed if we reduced suction or added water, and eventually you would approach a degree of saturation of 1. But you can zigzag between these two lines on what are called scanning curves, and they are slightly hysteretic, and there are an infinite number of those. So we have this complicated arrangement between drying, wetting, and something in between as you're moving towards a main drying or a main wetting curve. But this is the most important property of a tailings that we must determine if we are trying to characterize its properties when it's unsaturated. There are standard laboratory techniques in which we can do this, and most universities are equipped to do it, and also some consultancies as well. But we can simplify that relationship into some nice straight line segments when we take the logarithm of suction and the logarithm of degree of saturation. So logarithm of suction is down here on the right at the bottom, and the logarithm of degree of saturation is up here on the left. So saturated initially, as we increase suction, we dry the tailings out and move down a main drying curve. As we wet the material, we move along the main wetting curve, and we can have some straight line segments representing our scanning curves. Now there are two key points up here. This S subscript AE, this one here, is what we call our air entry suction. And that is this line being extrapolated up to a degree of saturation of 1, and it's that intercept. And this other line here, S subscript EX, is where that suction is called the air expulsion suction. It's where this wetting curve is extended up to our degree of saturation of 1. So these are two key properties that tell us the positions of our main drying and wetting curve. And the slope alpha is a material constant that we measure in a laboratory, as is beta, the slope of the scanning curve. So we can realize that straight lines in double log planes are power laws up here on the right. So our degree of saturation scales with suction over either air entry or air expulsion to the power alpha. Now there is a companion set of lines which define chi. So I've plotted two quantities on the vertical axis, the natural log of suction, degree of saturation, as well as the natural log of chi. And chi has another set of straight lines. Down here is our main drying, and up here is our main wetting. So if we're undergoing a main drying process and you're at this point on the water retention curve, then you go down and find the point where you are on the chi line for its main drying curve, and then you can go across and quantify chi. So this couples together the degree of saturation with chi, using the different slopes of the lines, but they have the same intercepts, S subscript AE, S subscript EX, up here where our degree of saturation is 1. So there's a little bit of mathematics there that you just need to look at and study and think about, but it's based all on these power law expressions. Chi also has a power law with our suction ratio, and I've just put in some typical numbers here on what the different constants could be. The omega, which is a slope of these drying and wetting curves for the chi relationship, we know is always around about minus 0.55 for every type of soil or tailing, so it doesn't matter. But alpha can vary between a range, as can beta, and so on. Now there's another important feature here, and that is the void ratio dependence. We know that a denser material has a lower void ratio and therefore smaller pores or smaller voids. So these air entry and air expulsion suctions, where air breaks into the tailings or is expelled outwards, depend on that void ratio. Obviously, if you have a large void ratio, you have smaller pores and you need a larger suction for air to then enter the tailings and start to desaturate it. And that's what this equation does here. So we capture the void ratio dependence with this E void ratio power law. There's a constant multiplier C1, which we determined from our laboratory tests. And this exponent ds happens to be a property called the fractal dimension of the particle size distribution. Tailings and well-graded soils are fractal. This is a peculiar phenomenon that results from the grinding processes used to create them. It means they have a special mathematical pattern to their particle size and pore size distribution. And it lets us do some very neat mathematics. We can quantify things like surface area of particles and pores, volumes of particles and pores, and we can interrelate those together using some nice mathematics and theory. And it leads to these expressions. So these are not guesses or empirical fits, they are derived from mathematics. The exponent ds, although it relates to the particle size distribution, it now also features in the air entry or the air expulsion expressions, which are primarily controlled by the pore size distribution. And we've connected particles and pores by the fact that they must have the same surface area inside the material. The paper is this one down here, 2014, if you really want to learn more about fractals. Anyway, we can do some neat mathematical manipulations and show that this chi-s term can now be related to degree of saturation, or in this case, gravimetric water content and specific gravity, according to this expression. And we've got the slopes of the lines, omega, alpha, the fractal dimension of the particle sizes, ds, and so on in there. And this constant multiplier is either C1 or C1 times C2 or some square root of those if you're at the midpoint of a scanning curve. So now we can quantify how chi-s changes, if our moisture content changes, or if our void ratio changes using this very simple expression. Very powerful when we start to look at strength and stability problems for a variety of conditions. This is some of the information around fractals. If you imagine in an idealized setting, we have 3 circular discs touching at points here, here, and here. And then we insert another circular disc, the maximum that is able to fit. And in the spaces that remain, we insert 3 more circular discs. and we repeat that process forever, we have what's called an Apollonian packing, which is fractal. And eventually you remove all the voids and you end up with complete solid made out of this granular material. Tailings have this particular property as well. You can randomize it, you can go into 3 dimensions, you can introduce particles of different shapes, but it doesn't matter, that the same properties apply. Likewise with the pore size distribution, you can start with a solid, break it into 27 smaller cubes, and we remove 7, so 6 from the faces, plus 1 from the center. And of the 20 that remain, we break those into smaller cubes and again repeat the process of subtracting out some of the solid. And we do that all the way down and we end up with this fractal pore size distribution, and it's called a Menger sponge. So these are just some idealizations, and tailings have this property. It means that when we plot the double log particle size distribution, if you plot log of particle sizes on the vertical rather than linear, sorry, if you plot the log of percentage passing rather than linear against the log of particle size, you'll see a straight segment, at least for a couple of log scales, and that indicates that the tailings is fractal. And the slope of that line is 3 minus our fractal dimension, which is a property that you then feed into those other expressions for air entry and air expulsion. So here are the water retention curves for 2 different tailings, which I'll focus a bit more on later. Top left is for a gold tailings. Now notice that suction has been non-dimensionalized using the air entry value, degree of saturation, double log, purely dimensionless presentation. The void ratio dependence is captured through the denominator here on the horizontal axis. Our main drying curve is down here. Top scanning curve is this. It's physically impossible to be in this region because you start from a degree of saturation 1, you dry, and to get to the drying curve, you must move along a scanning curve, and that happens to be this one. We call that the top scanning curve, and then you stay on that main drying curve. It's physically impossible to get into this region. Here's a main wetting curve and so on. Here's another water retention curve. This is for a copper tailings. Same basic setup. So chi in our degree of saturation, or more specifically air entry, air expulsion suctions, they depend on our tailings density as well as our tailings type. Generally, air entry, air expulsion suctions increase as the pore size reduces or as the material becomes finer or denser. And these are some typical numbers on what they are for different materials. Between 1 and 8 kilopascals for a very sandy material, but tens of kilopascals and possibly megapascals when you start to add fine materials and especially clay. Now this is another very important graph. It shows how this chi-S quantity varies with depth inside an unsaturated tailings. Let's firstly look at the phreatic surface. That's this horizontal continuous line here. That is where pore pressure is 0. So below that, I've assumed the water is hydrostatic, so we have a linearly increasing water pressure. Above the phreatic surface, we have capillary rise. The tailings is a bit like capillary tubes, and it sucks water up into it, and it stays saturated. And that is this region here. And the height that the water rises is this quantity S subscript E over the unit weight of water. This SE is either your air entry or air expulsion suction, depending on whether it's a drying process or a wetting process. And that capillary rise section can be, well, the theoretical maximum is around 10 meters, and that is when you would get cavitation, because the water in this sort of free body setting will cavitate when the pressure goes below 1 atmosphere. But in reality, it's a little bit less than that, the maximum. It's probably around 7 or 8 meters. And that is because cavitation will occur sooner than 1 atmosphere because you have impurities in the water, things like salt and grit and dirt, things that make cavitation occur a little bit more quickly than in the pure scientific definition. And then above that capillary rise section, we start to become unsaturated, and we have a nonlinear Chi-S profile with depth that depends on infiltration, evaporation, and various other factors. But it's saturated all the way up to this top of capillary rise section, but we just have a negative water pressure inside there that we must account for in all of our analysis and CPT interpretations, especially if it's extensive, like multiple meters. Now I'm going to take a slight divergence here for a minute and introduce a little bit of other research we did on how to put suction into strength and stability problems. This is of general interest to all civil types of problems, not just tailings. We looked at shallow foundations, retaining walls, slope stability, and we solved all those problems using slipline theory. And that's a process where you assume the soil fails according to a perfectly plastic Moore Coulomb type criterion. But we can calculate things like bearing capacity and slope stability and retaining wall earth pressures and things like that by putting suction into the governing equations. In all of the problems we assumed cohesion varies with depth according to this function. So it has a value at the soil or tailing surface of C subscript 0, and then it changes with depth Z according to some constant K. And likewise with Chi-S, it has a value at the surface and then increases or decreases with Z according to whether this K term is positive or negative. So if we have this real sort of curved profile of Chi-S, we can approximate it at least for a short section to have this straight line obeyed by this equation here, and then we can apply these theories. And when you use slipline theory, you identify dimensionless groups which govern the problem. For bearing capacity, these are the important dimensionless groups. There's a V term, I've called it because it's on the vertical axis, but it's dimensionless. It includes the bearing capacity QU, and on the denominator we have a part which includes the cohesion at the soil surface, the Chi-S at the soil surface, and then some surcharge as well. On the horizontal axis, the dimensionless quantity is F. It includes the footing width B, and this is now where the total unit weight is included, but also now the rate of change of our cohesion, KC, and suction, Chi-S feature in that. The third dimensionless group is our friction angle. And you can present a graphical solution to the bearing capacity problem. That's what these solid black lines do. They're for different friction angles, different values of dimensionless F, different values of dimensionless V. And this now enables you to quantify bearing capacity using a graphical technique. If you used a more classical bearing capacity equation from CIIGGUPC, for example, for 30 degrees, it's this dotted line just below the black line. And the small difference is due to the errors inside CIIGGUPC's theory. The errors are well known. The theory underpredicts the bearing capacity by a small amount because it uses superposition. It adds on the solution for purely cohesive material onto the solution for a purely frictional material, but doesn't do any interaction between cohesion and friction inside the theory. And that's why it's slightly approximate compared to the true solution, which is the black line. We do the same thing for slope stability. These are dimensionless groups. The F term is exactly the same as for the shallow footings. T is a slightly new term, unique to slope problems. It is essentially related to the angle that the slope makes with the ground surface up here, and it looks very different to the V term in the bearing capacity problem. But friction angle is the third dimensionless group. Again, cohesion and chi-s have been assumed to vary linearly with depth. But what these studies do is reveal a way forward for industry on how to capture suction inside these strength and stability problems. And I've called it the equivalent method. We have an equivalent cohesion that we must define, and it is our cohesion at the ground surface plus some part due to the suction at the ground surface. This is fairly well known. A lot of practitioners and academics already adopt this equivalent cohesion in their work. But what is not so well known, but equally important from a theoretical point of view, is that we must define an equivalent unit weight as well. So it's the true total unit weight plus some modifications to account for the fact that our cohesion and suction have a gradient with depth. And if we define both of those things properly, we capture suction entirely in the problem in a correct mechanical way, ensuring that the dimensionless groups do not change. So using these artificial equivalent quantities, the problem is still being modeled exactly because the dimensionless groups which govern the physics have not changed. The chi-s profile that we use from a practical point of view should be representative of the worst case. So if it's a wetting process, we should use the main wetting curve in some way. And what I'll show in a minute is that this is a much simpler way to now just carry on, use standard knowledge of mechanics and essentially a total stress analysis with these equivalent cohesions and unit weights. And we don't have to use any of the more complicated unsaturated soil features of a software, for example, which are becoming more prevalent in all these commercial packages that we see out there. You simply don't need them. This is much simpler, and I'll show how accurate it is in a minute. I must point out that this is only useful or valid when this chi-s value doesn't change a lot during the loading scenario. So we can assume, the value initially is also present when the structure will fail. This is only true as when we have more than about 15% of our volume occupied by air, and there's evidence for that. Or in other words, when our degree of saturation is less than, say, 0.5 or 0.7. And it doesn't matter if it's a slow or a fast loading event, that chi-s won't change much as long as we've got a lot of air inside the system. And I'll show some proof of that a bit later. This approach of equivalent unit weight is not new. It's exactly what we do for saturated soils. We can adapt those dimensionless groups and instead of and for a fully saturated state, we can realize that this K chi-s term can be interchanged with K, and I've put a little UW subscript, but it's the rate of change of water pressure with depth, which is essentially the unit weight of water. And when we put that inside our dimensionless group, you can see that we're subtracting gamma water off our gamma total to get an effective gamma. So this is perfectly consistent with saturated soil mechanics and how we solve these problems. We use an effective unit weight rather than the total. And the same is true for unsaturated. This is a little exercise I get our students to do at UNSW to prove that it all works. I give them a slope stability scenario, and I know the factor of safety is exactly 1 when we have these material properties and they correspond to this dimensionless group setting. Okay, so the total unit weight 18.5, cohesion 16.8, surcharge 228, chi-s varies with depth. So using this equivalent method, we can recalculate our unit weights and we get 18, our cohesion becomes 37. The pore pressure part or the suction part is now 0, so we're just doing a total stress analysis and our surcharge doesn't change. I can get them to put in some outrageous numbers, like a unit weight of 79, a cohesion of 162, surcharge of 1,000. These give exactly the same dimensionless groups up here, which govern the stability. And then I get them to put these last 2 scenarios into a software, and this happens to be Slide. It can also be Slope W if you wanted to do that instead, or some other limit equilibrium software. So this is using the equivalent method, unit weight of 18, cohesion 37, surcharge 228. Factor of safety of 1 comes out, as you'd expect. And this is the outrageous case, unit weight of 78.9, cohesion 162. Totally different looking, but in reality, exactly the same problem because the dimensionless groups haven't changed. And again, the factor of safety is 1. Now we'll get on to CPT and strength in unsaturated soils and tailings. This is really practical now. I'll start off just by giving a bit of a summary around what we know already for natural soils, sands, and so on. I'll talk about drainage conditions. These are really important, and then I'll show some examples and what we've achieved so far with unsaturated tailings around CPT interpretations, as well as instability and post-liquefaction strengths. Here we go. Very early on, 1987, using a very basic calibration chamber, they did some miniature cone tests at a range of degree of saturations in a sand. And they found when the degree of saturation is around 0.1, the cone resistance was roughly double that for the saturated case. So we know the suction is enhancing the strength and increasing the cone resistance. A little bit later in Perth, here in Australia, some people looked at cone resistances at the end of the wet season, that are these 3 black lines through here, as well as the end of the dry season. These are the open symbols over here. And you can see, you know, at the end of the dry season, suction will be high. At the end of the wet season, it will be very small and perhaps 0. That the suction is causing a big increase in your cone resistance, roughly by a factor of 2. We looked at another sand at UNSW using our calibration chamber. Here, suction controlled tests. This one's saturated on the left, but over here on the right, the suction was 200 kilopascals, and you can see that again, cone resistance is roughly doubled. The suction influences are especially pronounced when we have very low confining stresses or in shallow sections. They're still present at larger confining stresses. Here it's 100, unsaturated and saturated. There's still a big difference. But you can see that when the confining stress is small, the chi-s part has a bigger influence on the effective stress, and therefore you see a bigger change due to the presence of suction. We also did some work on a silty tailings, a silty sand. This is a well-graded material, just like tailings. Higher suctions, cone resistance was larger than what it was for the lower suctions over here on the left. So I've been researching this problem for 20 years, and we've done a whole lot of thinking and analysis especially around drainage conditions. We're trying to think about what is relevant and easiest to deal with in practice. It would be great if we could suppose suction is constant during the cone test, or in other words, it doesn't change from the initial value. Or even better, it would be great to assume that chi-s is constant. So we have a constant pore pressure contribution to the effective stress during the, so essentially a drained condition during cone penetration. But in reality, we don't have those. We've got a constant water content condition. The cone penetration occurs quite quickly. There's not enough time for water to escape or drain into the soil or the tailings. So we've got this kind of locked in water phase, which is neither drained or undrained. We explored this using cavity expansion theory. We looked at these three drainage conditions analytically, and the pressure required to expand a spherical cavity, for example, is roughly similar to the QC that we measure at the tip of a penetrating cone. In doing a whole lot of analysis and different soil types, we found that the constant suction, constant moisture content, and constant chi-s results were fairly similar. The differences weren't huge, and the constant chi-s was a pretty good approximation to everything, irrespective of what the true drainage condition was. The errors were always less than 30% and mostly less than 10%. So we said, well, that's enough from a practical point of view. Let's just assume chi-s is constant whenever we do a cone penetration, and it will simplify all our interpretation methods that we develop. Now, this is only the case when the volume of air is around about at least 15% of the overall volume of the soil or the tailings. The volume of air as a function of the total volume is important because it is the fraction of the tailings which can change in volume during a penetration. It's a more useful indicator of compressibility than degree of saturation or void ratio on their own, and that's why we use that instead. Only the air phase can compress or change in volume. Air is very compressible, whereas the solid and water are very, very stiff and almost incompressible. So here are some of the sand results interpreted. You can do it in one of two ways. We can use the Boldy approach, where we plot cone resistance as a function of the mean effective stress raised to a power, and then a relative density part as well. And you can see saturated and unsaturated tests for a given relative density are unique in this plane. The solid is saturated, the open symbols are unsaturated. So nice uniqueness there for our sand. You could use a state parameter approach instead, this one from Bean and Jeffries using K and M, and you get a slightly different type of interpretation. It's got a state parameter psi term inside there. But these two expressions are actually the same thing. They're just rearrangements of each other. You can go from one to the other, obeying soil mechanics perfectly. For example, if we put the expanded form of the state parameter inside here, you can show after some rearrangement that the mean effective stress is again raised to a power, and the exponent happens to be 1 minus lambda times m. So here's some examples of application in a Sydney sand. 2 QC values obtained for different values of mean effective stress, but equal relative densities, can be linked by simply putting them as ratios and raising the effective stress ratio to a power of 0.85, that exponent that we've determined experimentally. We can do this for 2 tests conducted in unsaturated cases and work out how the chi-s part is changing as we go from one cone result to another. Or we can also relate an unsaturated and a saturated result because we have identical trends for both cases. So let's look at an example. Let's suppose we have a cone resistance of 4 megapascals. The total stress is 25. Well, let's suppose chi-s is 25. We can put those into the various expressions and come up with a relative density and a friction angle of 39 degrees. Soil behavior type 1.6, cyclic resistance ratio 0.35. If we ignore suction incorrectly and suppose our effective stress and total stress are the same in 25 and redo it, we get an effective friction angle of around 43 degrees and a resistance ratio of 0.6 or more. You can see here that failing to account for suction can overestimate our strength and make us think the soil is denser and stronger than what it truly is. Here's another example where I've back calculated the chi-s at that Perth sand site using this ratio. This is the chi-s profile plotted over here on the right. Now, I must point out that I'll go back to the Sydney sand graph. We're very lucky here that the saturated and unsaturated data overlay each other perfectly in this plane, and that's because there is no suction hardening present. For a sand, a clean sand, any suction hardening, which is the shift of the critical state line, if it is present, is very, very small and can be ignored. It's only when you start to add silt and other smaller grains do you see a significant suction hardening that needs to be accounted for. So the case for sand is much simpler than what we have to deal with when we move into tailings and silty materials. This is the silty sand where I'll highlight that. The silty sand has a suction hardening present. We still see this boldy type expression for our cone resistance as a function of our mean stress raised to a power. This is only when it is unsaturated. And the same equation will not work if the soil was saturated. And that is because of suction hardening. We have quite a different set of expressions that would apply. So we need to be careful when we adopt this approach of using a ratio of cone resistances and mean stresses. We can only do it if in both examples, in both sets of data that we're comparing, that the two quantities are for this unsaturated state. In other words, we can't do it for an unsaturated and a saturated one down here on the bottom. There are some implications with classification. Let's look at the Sydney sand data: solid, sibbles, saturated, hollow, unsaturated. And I've correctly put chi-s into the effective stress term here, used to define our capital Q. The cross symbols have been plotted incorrectly on purpose by ignoring chi-s or assuming it is 0. So these are erroneous data points. And I wanted to explore how badly we would get our soil classification. You know, how wrong would it be if we ignored suction? And with the sand, it's not so bad. Even when we ignore suction, they're always locating up in region 6, and they're always showing a slightly or a fairly dilative material for the results that we've generated. That's not always the case though. This is a marine sand with up to 8% fines. So this is a hydraulically deposited fill used to construct an airport in, I think it was in Japan or Hong Kong. I think it was Hong Kong actually. They've got CPT data below the water table. So that's the black symbols, as well as CPT data above the water table where it's unsaturated up here. And I've intentionally ignored suction when I plotted the unsaturated data. And you can see that from the same deposition process, the correct interpretation shows the soil is a material type 5 or 4, and slightly dilative, perhaps borderline dilative contractive. So there's a small risk there with liquefaction. But if we ignore suction, we falsely see that the material is type 6 and very dilative. And if that material were to become saturated later by the water table rising, it would lie down here somewhere, but we have no advanced warning that we could have a problem with liquefaction because we've ignored suction. You can also do things like compute the cyclic resistance ratio. When it's saturated, it's fairly low, 0.1 to 0.18, but doing it incorrectly by ignoring suction in those other data points, you falsely see that it's very large, around 0.6. And that might give you a false sense of safety that would not be true if the material were to become saturated later. Now let's look at tailings. And again, I'll mention the industry partners, Anglo American, BHP, Freeport, McMoran, Newmont, Rio Tinto and Teck. It's an Australian project conducted at UNSW as well as universities of South Australia, Western Australia, Wollongong, and also the Future Fellowship that I've been given. So these are the key contributors. There's 6 of them. This is mainly just on the CPT parts. The other researchers are looking at different things, so yeah, lots of contributors and funding, and thank you very much for that. The 2 tailings I'll just look at today are a copper and gold tailings, almost identical grain sizes, both nicely fractal. Now, all the details can be found in this GeoTechnIQ paper, and GeoTechnIQ have been very kind, and they've made that freely available online, so you can go to the website and download it without paying. So add that one to your personal library. It's a very sort of comprehensive and also a very practical paper. So I hope you find it useful. We've talked about the critical state lines already for the 2 materials and how there is suction hardening and a shift, so I won't go through that again. The water retention curves of the 2 materials we've already talked about, so I won't go through those again. Now here are the CPT results. And we've conducted these experimentally using 2 calibration chambers at 2 universities, UNSW and UWA, Western Australia. The UNSW chamber is very large, as you saw in the photo, but the UWA chamber is a miniature chamber. It holds samples which are only 200 millimeters in diameter, and it can sit on a laboratory bench and operated by 1 person without having to lift heavy things. And they used a miniature cone to push into it as well. So here's our results. The solid symbols are saturated tests. The hollow symbols are unsaturated. Cone resistance normalized in this way, plotted against the initial state parameter. The saturated and unsaturated data obeys a unique line. This is for the gold tailings. This is key, and this was a big discovery for us. The saturated tests, I must say, were performed in the miniature chamber, and they were conducted very, very slowly, pushing the cone in at, I think it was 0.4 millimeters per second. So we have drained conditions around the cone tip all of the time. The unsaturated tests were performed with fast penetration rates in a much bigger chamber. But in both cases, we see uniqueness. And I'll explain why in a minute. Basically, the unsaturated tests are being conducted also in a drained condition. And I'll explain why that happens in a minute. Incidentally, this red line is what you would recover using the Bean-Jeffreys correlations and lambda 10 used to compute those, which has a lot of scatter in the data and the charts used to get those. It's called a preliminary screening approach, but here's just a warning. It can give you a very unsafe predictions of what the state parameter should be. You know, if we get a cone resistance of 10 read across you might falsely think your state parameter is 0.05 when truly it's maybe 0.25 or 0.3, okay? Now, the other data on the right here is for the copper tailings. Again, saturated, drained results, solid symbols, unsaturated is the hollow symbols. Again, uniqueness. There's a small scatter, but that's typical of other CPT data. So those unsaturated and saturated tests all collapse onto a straight line because they're all performed under a pseudo or a drained condition. There are three other data points I've shown with these crosses. These are for unsaturated tests, and they don't lie anywhere near the main trend. And that is because the volume of air present in those three particular tests was very low, less than 15% of the overall volume. And that means that as the cone is being pushed in, we have this complicated scenario where the air is partly compressed and the tailings undergoes this partially drained, partially saturated behavior, causing it to deviate quite significantly from the other unsaturated data where the volume of air was much larger. What is required for uniqueness in our saturated and unsaturated results? Well, the key thing is that we need at least 15% of air in the volume. And that means that as you push a cone, there's enough air present that it is able to compress in volume because it's very compressible, so that the tailings skeleton around the cone can deform freely as though it was perfectly drained. So we have the free ability of volume change in this unsaturated setting that is very similar to what you see in a drained test for a saturated state. And that's why our cone data for those two sets of scenarios, saturated and unsaturated, are forming a unique relationship. We've got drained conditions in both cases. And it's only when the volume of air is less than that 15% do we have this partially drained, partially saturated scenario causing a deviation from the main trend. And we don't yet really know how to address that condition. So we're working on that now. So the saturated tests were performed slowly, so we have drained. The unsaturated tests were performed with large air volumes, so they were also drained, and we have uniqueness. With the unsaturated, the penetration rate is not so important. You can do a fast cone test or a very slow one, but the volume of air is sufficient so you'll get a drained response in both cases. Now, I must also note that the state parameter on the horizontal here has been determined using those relocated critical state lines, accounting for suction hardening. That makes this approach a little bit difficult to deal with in practice. I'll show a way around that in a moment. But firstly, let's just compare our laboratory results to field results. Two sets of cone test results are shown here. CPT1, the black line is for a standard penetration velocity of 2 centimeters per second. CPT2, nearby, exactly the same, except for a 1 meter section here where we slowed the velocity down to 0.4 millimeters per second. And you can see that with the slower CPT, the pore pressure measurements were essentially the hydrostatic values. We think this is our phreatic surface here, a hydrostatically linearly increasing pore pressure with depth is shown, and you can see our pore pressure measurements are quite close to that. It's only when we performed our CPT quickly, the black response, CPT1, did we see a deviation from that hydrostatic, and we think we have a purely undrained response due to that particular velocity and coefficient of consolidation for that test. So our previous correlation on the slide where I've overlapped the saturated and unsaturated data, lets us recover a state parameter from this data as long as drain conditions prevail. So that can only be applied for this 1 meter section in CPT2. But what we can do is link those state parameters to the cone measurements for the undrained scenario to then determine another correlation relevant to when undrained penetrations apply. And that's what's shown over here on the right. These dots through here are our normalized cone resistances plotted against state parameter determined using this correlation when undrained conditions apply. And you can see that the dashed line through that has, again, a nice unique straight line relationship, but it's very different to the one you see for drained conditions up here. So our correlation between this normalized cone resistance and state parameter depends very much on whether you have a drained condition or an undrained condition prevailing. And that is well known in academia, but it's perhaps not as well known in practice as it should be. The correlation that you use in this plane depends very much on the drainage condition inside the tailings. And if it's a partially drained condition, you'll have a separate correlation again. We've plotted the void ratios that can be extracted from the state parameters and related those or compared them to void ratios recovered from piston samples in the tailings dams. They're the vertical grey lines through here, and you can see good agreement is found between our correlation and the measured values. I've also plotted over here on the right an estimation of what the state parameter will be if the water table rises or the phreatic surface rises inside the tailings dam to the surface. So this would represent a worst case scenario or perhaps a future scenario where the water pressure or the water regime changes. And you can now kind of quantify what the state parameter would be at that point in time. And I'm assuming that the void ratio doesn't change between the current result and that future scenario. It might a little bit, but not by a large amount. So this is kind of a good tool that you can use to forecast and plan for future risks that might prevail. Now, I must show a couple of other things in the shallow portions of the unsaturated sections of the penetration. Immediately above the phreatic surface, by a distance of around 2.8 meters, you can see that the cone is trying to measure negative water pressures, as it should be, and that's due to this capillary rise phenomenon. The water is in tension, and the cone is picking those up reasonably well. And it's only when the water pressures become really, really low, or there's a lot of air in the pore space that the material desaturates, and your cone doesn't measure anything sensible. But you can see how we can start to segment the profile into a capillary rise section, a saturated section, and then an unsaturated section above the capillary rise. Here's another set of results. This is in the copper tailings. This is all unsaturated. The real cone resistance is down here. We think from the results where there are spikes in the pore pressures that we have localized saturated layers or nearly saturated layers. So we've taken those out of the analysis and just focused on the sections where we weren't measuring pore pressures that made any sense. And we then back calculated void ratios using the correlation, and it compared them to block samples and so on. And you can see that you get reasonable agreement. And likewise, I've plotted a future state parameter if you think the material were to become saturated later. Like I said, the state parameters that are central to these interpretations require knowledge of the critical state line locations and suction hardening. I realized to characterize that properly, you need a whole lot of triaxial tests and special equipment, and that probably won't become routine in practice. So here's an alternate presentation. We can normalize our cone resistance against the total mean stress, plot it against void ratio for different moisture contents, and group the data according to different mean stresses, and you come up with these plots. This is for the copper, the gold tailings, this is for the copper tailings, and you'll see something similar whatever your tailings type. This can be used in practice. So you know your cone resistance, you know your mean stress. If you can recover a moisture content from an undisturbed sample or a borehole, you can then estimate your void ratio, which is really useful to you from a stability and strength point of view. Now, to draw these are theoretically drawn using the correlations that we established from the laboratory tests. And I've also assumed that the hydraulic states are at the midpoints of scanning curves. So we're not on the drying curve, we're not on the wetting curve, we're somewhere in between. And I think that's the case most of the time in practice. It takes an extraordinary wetting event to end up on the main wetting curve, and it takes an extraordinary drying event like a very long drought. Perhaps you're in the middle of one now. I know South America is very dry, but you need that extraordinary scenario to end up on the drying curve. Under normal climatic conditions, you're somewhere between them, and the midpoint of the scanning curve is a reasonable assumption. Now, the evidence for this is limited. It's a view held by a lot in the unsaturated soil mechanics community. But, what we do know is there's one example here. This is for an unsaturated soil slope in New Zealand, where we monitored the hydraulic state for a period of 2 years. And we found that even though there were wet and dry periods during that 2-year period, the hydraulic states were nearly always on the scanning curve. And that's a reasonable assumption that we can make most of the time. I won't go through that. I'll quickly talk about instability and post-liquefaction strengths when we're unsaturated. These are some triaxial test results. Initial degrees of saturation, 0.65 to 0.75. And they're closed system tests. So I've deliberately closed the valves on the sample so water and air cannot escape or enter the sample. So this represents a fast loading scenario that you might have in an unstable scenario inside the tailings. And you can see that we get a fairly classical sort of looking response. We get a strength increase, some kind of peak, and then it softens off to some critical state residual value. Because air is compressible, you get a little bit of volume change or void ratio change inside the tests. We can link together air pressure change and effective stress and volume change using Boyle's law. So the absolute pressure of the air times the volume of the air must be a constant. So that lets us do some simple mathematics and mechanics linking all this together. We looked at instability lines. So these are points where Q peak was attained, sometimes called collapse lines. That Q peak, when unsaturated, is also very close to the point where second order work becomes zero or instability becomes possible. And you can see that these instability lines now depend on the degree of saturation, which is shown in these parentheses up here. We also looked at a variety of K0 conditions, load paths applied during the triaxial loading, and initial stress states. But you can see that although there's some small scatter here, degree of saturation is the main parameter that controls our instability line. We also looked at a strange load path that from a triaxial point of view, but it's very similar to what can happen inside of tailings. We held our total stress as constant, but we reduced suction. So our initial state was over here somewhere. we reduced suction so that the stress state moved towards the left, and we picked off the point where it became unstable. And we found that in a couple of cases, these black lines in the inset, so the black dots, did not locate close to where the other instability lines were. So there is a load path dependence here to the instability for that we need to explore a little bit more and then translate into practice. Here are some post-liquefaction or post-instability strengths, and I've plotted them in charts that resemble what we do for saturated cases. Initial state parameter, strength ratio normalized against the initial effective stress. The dots are experimental results. The numbers next to them are the degree of saturation. And this is the theoretical line through there for a degree of saturation is 0.65. 0.85 is through here. Saturated is through here. So you can see that you can still get quite low strength ratios even when your degree of saturation is around 0.85. And that would be a problem in most practical cases. In fact, some of the big mining companies now are very aware that you only need a degree of saturation of 0.8 or more for liquefaction to become a risk, even in an unsaturated tailings. And this validates that stance that those mining companies are taking. Now, again, the state parameter here requires knowledge of suction hardening, as does the effective stress here. It requires knowledge of suction. So I've replotted it all using a modified state parameter, which is defined just using the saturated critical state line and using a total stress rather than effective stress. So you don't need suction to apply this particular chart. And again, yeah, degree of saturation 6.5 over here, 0.85 through here, saturated here. Much easier to apply in practice. So in summary, if we go back to our suction profile with depth, what do? Saturated below phreatic, simple, use saturated soil mechanics, but also in the capillary rise section, we use saturated soil mechanics, but we must account for the negative water pressure in the effective stress, which will be hydrostatic in a linear extension of what happens below the phreatic surface. But inside that saturated region, established concepts apply. Skempton's A and B parameters. We can determine an undrained shear strength by dividing our cone resistance by N. We can apply the Bean-Jeffreys type state parameter interpretations. We can define undrained strength ratios. As long as we correctly put the negative water pressure inside the effective stress. Very important to do that. So often I see that in practice people assume the pore pressures are 0 in that region. That's not the case. Put in the negative number. Above, up at high regions, as long as we've got less than or more than about 15% of air in our tailings, we can use unsaturated soil mechanics, this equivalent method of a cohesion and unit weight, and we essentially adopt a total stress analysis. And the tailings will behave as though it's drained, whatever the loading rate. And we can then apply these alternate Bean-Jeffreys type correlations. But this is the region where we still don't really know what to do. It's immediately above the capillary rise, where the air is less than 15% of the overall volume. So what can we do until we resolve this? Well, I propose that we can use either unsaturated soil mechanics, very complicated, very fully coupled, partially drained analysis. Maybe that's not practically achievable. Instead, perhaps look at a total stress analysis, use strength parameters defined using total stresses, but be very careful now because there is a load path dependence to those total stress strength parameters. So whatever you do in the laboratory to measure those, the load paths that you apply must be quite similar to what you expect to have in the field. just before I close, this is just some practical observations that I'm seeing in Australia and other countries on what is happening on using unsaturated soil mechanics in practice. The companies are engaging universities to determine water retention curves. That's great. In strength stability, they're using this equivalent cohesion, but they're forgetting or not aware that they should be using the equivalent unit weight as well. But they're making lots of mistakes. They're assuming that it's total suction that contributes to strength. That is the matrix plus osmotic part. But the matrix, which is the capillary part, is really the main contributor, especially when you don't have much clay present in the material. They don't consider hydraulic hysteresis. In other words, when they're designing for a worst case scenario like a wetting event, they suppose the hydraulic state is on the main drying curve. Don't do that. Instead, you should be assuming it's located on the main wetting curve. They don't realize that suction should be multiplied by chi before it's added into the effective stress. And yeah, a few other things. These devices, MPS6, Teros, they're quite good to measure suction inside a soil or tailings, but we must remember that they're only used or there's a calibration curve for those which is only valid when the soil or tailings is undergoing a drying process. If you're burying those in your structure and you have a wetting event, the calibration curve is useless and can't be used. Be careful with your language. You can't calculate an undrained shear strength for an unsaturated soil. That's a saturated property that represents a constant volume condition. It has no relevance to an unsaturated material. Piezometers in unsaturated soils, be really careful that they're buried in sections where the suctions are not too large, because a large suction will desaturate the piezometer tip, and then when you resaturate the soil later on, your piezometer is faulty and won't measure anything that is useful, and so won't properly trigger alarms. And also above the phreatic, in that saturated region where we have capillary rise, please use negative water pressures. And yeah, they're the main things. Look, here are the key messages. Use the equivalent method when our volume of air is larger than about 15%. Capillary rise, use a negative water pressure. When our air volume is larger than 15%, we can use a total stress, method. That's all good. And yeah, I won't go through all those in detail. Look, here's some further reading. These are really practical papers up here at the top, and these are some of the underlying theoretical concepts if you want to learn more about those as well. Like I said, the top one there is freely available right now, so you can log and download that one straight away. Okay, look, I'll stop there.
Thank you so much, Professor Russell, for this amazing presentation.
That's okay. It was a pleasure.
We consider this has been a very interesting topic, and we're pretty sure that the audience has enjoyed it and learned from this experience because of you and all your knowledge. So now we can pass to the questions and answers section, if you don't mind.
Sure.
Okay. Let me start with this one, which is, which software would you recommend for tailing modeling?
Which software for tailings modeling? What sort of modeling are we talking about? Look, limit equilibrium, I mean, they're all the same. So slope W, slide, I'm not sure what the common ones are in South America, but they should give you the same answers. But if you're doing a fully coupled finite element, finite difference analysis, which is more advanced, and Plaxis or FLAC or some of the others are fine. But whatever the software in those more advanced scenarios, the outputs are only as good as your input constitutive model. You'll have to use something as a constitutive model. Some of the main ones programmed into those softwares are there's the HSS model, the hardening soil model, I think it's called. There's the NGI model, and to be honest, without being offensive, these are some of the less beautiful models out there. they're very complicated and ugly, and the input parameters are very strange to understand what they mean physically. But the reality is they're popular, and I guess we just have to teach people how to use them properly. Especially when there's cyclic loading, be really careful that your constitutive model can reproduce a cyclic response that you see in a triaxial or a simple shear test. Often I'm seeing the constitutive model remaining very, very stiff for 20 cycles, and then suddenly it fails and you get a large deformation. But in the experiments, you get a very gradual deformation building up through all of the 20 cycles, and you want your constitutive model to do that as well. And this obviously takes an experienced person to do it, but yeah, there's some of the things to look out for.
Thank you, Professor, for your answer. We have a next one, which is, how can we obtain the partially saturated post-earthquake shear strength on filter tailings?
Yeah, look, good. The earthquake loading, we're working on that now. So the triaxial data I showed you is more for a static liquefaction scenario, but maybe like for saturated, the unsaturated static liquefaction and cyclic liquefaction is similar strengths. We don't know yet, but we're working on it. So, and it's those last slides that I showed. If you know, you can still get strength ratios of 0.15, 0.2 quite easily when your degree of saturation is 0.85. And that's what you should be putting into your dry stack calculations. Yeah.
Really, really interesting engineering. Okay,
yeah.
We have the two last ones, so we can answer these. As an engineer or with all your experience, what do you think has been your biggest challenge?
Look, this is a good question. I started engineering thinking I was going to work in industry and build bridges and skyscrapers. And then I discovered geotechnical engineering, which is much more interesting. And but I've always been very practical and industry focused. And so when I do my research, I try and produce things that people can use in industry. And that is really hard to do. You will see academics, researchers produce very fancy theory that industry can't understand and will never use. And so it's just doing both. You need to do the advanced theory, but then you need to reframe it in a way that industry can understand and use, and that is the hard part.
Thank you, Professor. Really interesting answers. And the last one that we have is, what could you recommend to civil engineering students to wish to specialize in Silty Tailings? We have an next one. This is
what would I recommend? I think it's a sector that needs very, very good engineers and very, very smart people. So please do it. But you need to be strong at mechanics, soil mechanics, even saturated soil mechanics. You need to be very, very strong. And then you can add in more complexity with your unsaturated soil mechanics later on. But look, it's a great discipline. It's a great area to work in, and we know that there's going to be more and more activity in this region for as tailings dams get bigger, and unfortunately as more failures happen. So we need good people to get in there and do it well. Yeah.
Thank you, Professor. And now we have another from the audience, which says, for the tailing industry, should we start to calibrate the velocity of penetration of CPTU before testing?
Absolutely. The velocity, or more important, the non-dimensional velocity is important. You need to know if you're undrained, drained, or somewhere in between, and you can do that using the coefficient of consolidation. You know, it's velocity times diameter divided by CV, the coefficient of consolidation. And you can do other things like change the velocity in your testing just for small sections, not everywhere, just for 1 meter here and 1 meter there, and to see if velocity has an influence on the results. And be very careful when you apply the Bean-Jeffries chart to get K and M, because that chart ignores the velocity. And so your velocity might be very different to the ones used to draw the dots on that graph, and that will cause some big problems. And so it's better to establish K and M independently using good quality field data. So if you can do cone testing and have nearby good knowledge of the void ratio, you can then draw your own relationship between cone resistance and state parameter and come up with your own correlation that you should then use everywhere. And that would be much more reliable than the charts in those textbooks.
Answer, Professor. We have a comment from the audience also. We say, excellent presentation, Professor Basel. And a question which is, how reliable is this dissipation test in a partially saturated zone to estimate the saturated hydraulic conductivity? Is there any correction in case of
yeah.
activity?
At the moment, you can't do it. I mean, you can do it, but we have no way to interpret the results. Firstly, when it's partially saturated, I'm not sure if the pore pressure reading is reliable and what it means. There are some people in Italy trying to develop a special filter on the cone, so you can measure negative pressures, and then do things like dissipation tests more reliably. But we haven't even got the hardware technology resolved just yet, so we can't do it. I mean, we can solve it theoretically, but you can't do it practically. So we've got nothing to compare the theory to, right? So not yet, anyway. It will take some time before we can resolve that.
Thank you, Professor, for all your answers. We have also a comment which we thank you, engineer, for your presentation. And it's in Portuguese, actually, for your time dedicated to this presentation. And now, once again, thank you very much, engineer, for your excellence. Ponents here, all the members of our GeoUPC student chapter are grateful for agreeing to share your valuable experience and teaching with us. On the other hand, we want to leave you with the invitation to participate in future conferences with us. And we thank you once again for your brilliant participation and wisdom supporting us in this Congress. Wishing you all the success and many blessings. If you would like to share some goodbye words, we are all ears. Hear you.
Okay. Now, look, thank you very much. And look, I'm really glad that there's a good audience here, and you're all interested. I can send you the PowerPoint slides so you can circulate those. Like I said, the whole world is in this problem together. It's not just it's not just South America, Peru, Chile. It's Australia. It's Africa. You know, we all need to work together on this. And you know, if you want to do PhD studies or more research, please get in contact with me. Even if you're a student in South America, you can come and visit me in Sydney for a period of time. Also, if you're in industry and doing some consulting work and you need a little bit of help with dealing with unsaturated mechanics, please contact me and I can help. Sometimes it only takes me a few hours to help you with a big problem and prevent you from making mistakes. Okay, so it's only a small increase in your budget. It's not a big problem at all. Okay, so look, good luck, and yeah, feel free to reach out and contact me in the future. Okay.
Thank you so much once again, Professor. We're really glad to hear you and your wisdom. So we thank you again for this.
All the best. Okay, have a good evening.
Wishing you the best.
Right. Bye.
See you then.